Czy można znać się na wszystkim? Od razu nasuwa się myśl, że jest to niemożliwe, ale ja znam dzisiejszego gościa i wiem, że jest to wykonalne. A wystarczy, że obiektem badań jest wszystko, co tylko istnieje. Wszechświat. Jak wygląda, jaki ma kształt, jak się zachowuje, dzisiaj się tego dowiemy od specjalisty. Zapraszam na kolejny odcinek podcastu Wgryzamy się we Wszechświat. Profesor Boud Roukema, bardzo mi miło. Cieszę się ogromnie, że mogę dzisiaj z tobą porozmawiać. Od razu chciałbym zadać pytanie, jak wygląda Wszechświat, ale zdaję sobie sprawę z tego, że to jest pytanie kategorii zadaję i już przez godzinę można posłuchać odpowiedzi, ale może da się cokolwiek na ten temat powiedzieć. What does the universe look like, mainly?
What does it look like? Well, okay, that's a very broad question. Based on the 20th century and 21st century observations and understanding of the universe, we have a model of space-time. So it's space and time together. It's a mathematically self-consistent model. And this has properties. Well, the spatial part has shape, so it has curvature and topology. And if we separate space and time, then the spatial part is expanding. And we have lots of observations and constraints on that. And just to get us started on the model, it's a model of space-time with shape, with curvature and topology. And after that we have to get into more details.
Czyli mamy wszechświat, jesteśmy w stanie go opisać w sposób jakiś matematyczny, ale my wiemy, że w tym wszechświecie jest jakaś materia, są galaktyki. Jak one są rozłożone w tym wszechświecie? Czy są jakieś skupiska, czy są jakieś przestrzenie, gdzie nic nie ma? Jak wygląda tak okiem?
Well, the first thing is that because the speed of light is finite, what we actually see through telescopes is looking backwards in time. And I have to join this together with a constraint from our current model, which is that the age of the universe is finite. And so we see back through epochs of the universe going to earlier and earlier towards this 0 point of time in our current model. And so to say what it looks like, I guess in terms of, with telescopes we look up at the sky in all directions. And so we look with optical lights. Today we also look with gravitational waves. We also look with all sorts of other electromagnetic radiation, such as radio waves and X-rays and gamma rays. In terms of galaxies, these are big bunches of stars. And so we see some places, in the recent universe, so not too far from us, we see galaxies, so these bunches of stars in some places. In other places, we see more or less empty spaces, as you were saying. And so the universe is rather, we say, inhomogeneous. So it's lumpy, close to us, on scales of, in astronomical numbers, we say hundreds of megaparsecs. In popular language, we can say hundreds of megalight years. And on scales of, let's say, thousands of, gigalight years or gigaparsecs, the universe is reasonably uniform. And then as we also go further and further back in time, the universe looks more and more uniform. And so this near uniformity is also what, let's say, half a century ago was just a hypothesis. And it was a hypothesis the universe is more or less the same in all directions. And it's thanks to that hypothesis that we were able to use this model of the universe being more or less the same. And thanks to this model of the universe being spatially more or less the same, at any single time, but changing in time, that enabled us to get this family of models which we fit to the observations and gives us this standard model. So the fact that we see these empty places and the galaxies at recent times, but it's uniform on big scales, that comes together with our model to give us our self-consistency of our overall model. So that was a very good question.
A jak opisać ruch takich ciał? Na pewno słyszeliśmy gdzieś tam prawo grawitacji Newtona, wiemy mniej więcej jak to działa, że wystarczy, że jest masa i te ciała się przyciągają. Jak to wygląda w takiej globalnej skali? Czy nadal to prawo Newtona jest wystarczające, czy nie do końca?
Okay, in fact that's a really complicated question. Okay, on small scales, Newtonian physics is a reasonably good approximation, and that's still the case. But the problem is that Newtonian physics, and in fact, later on we'll get to the context of Copernicus and Toruniu, which is where Copernicus was born. Newtonian physics assumes more or less an infinite empty universe on big scales and some massive objects on local scales. So if we stick to this, then Newtonian physics more or less works. But to go beyond that, the physics of the early 20th century, so Einstein's special relativity and general relativity, aim to have a more mathematically justified theory that is consistent with gravity and on small scales is consistent with Newtonian gravity. But on big scales, Newtonian gravity just doesn't make sense, because we don't have an outside universe and we don't have an outside empty universe. We have to talk about the whole universe. And so general relativity, in fact, is there is a key equation which is a local equation, so a mathematical equation, something equals something. In fact, roughly speaking, mass equals curvature. And the idea is we want a space, that's the general audience, we want a space which everywhere satisfies this equation. So mass equals curvature, more or less, at all places in space and at all times. And so on small scales, it's like Newtonian physics, but on the big scales, it doesn't make much sense. And let's say some of the paradoxes of Newtonian physics, this gets into quite a few different complex details, but there are many paradoxes of trying to do Newtonian physics on the cosmology scale, but general relativity finds neat ways of getting around that. But certainly on small scales to, let's say, tens of megaparsecs, that's more or less the case. And just to say one specific example of where Newtonian physics has a problem in the cosmological context is that our overall model, as I said, is more or less uniform, and as a function of time, it is expanding. Now, in the overdense regions, a galaxy or a cluster of galaxies is much denser than the region outside. So if we take the Newtonian approach, we assume that there is an empty universe on big scales, and this is more or less a good approximation. But in reality, it's not quite true. Now, with the underdense regions, as you were saying, the cosmic voids between the galaxies, they are less dense than the average. And so, in fact, compared to the average universe, they are expanding. And so, in fact, this is something like anti-gravity. And so Newtonian gravity only has attraction. It doesn't have repulsion. So, in fact, as far as I don't know if anybody has actually tried to do a Newtonian anti-gravity model to model what happens in voids, but qualitatively, it's certainly like anti-gravity. And really, we have to use, we use general relativity in these cases.
Czyli prawo Newtona jest wystarczające, ale w bardzo małych skalach. Jeśli chcemy popatrzeć na to tak globalnie, no to już musimy użyć.
And especially for the overdense regions. For the underdense regions, it's a problem because we don't have repulsive Newtonian gravity.
A jak się w tym odnaleźć? Ten wszechświat, on ma jakieś granice? Jest nieskończony, skończony?
Okay. The assumption of the model is that it's a space without edges. Well, without edges would be in 2 dimensions. Space is 3-dimensional. Okay, space-time is 4-dimensional, but the spatial part, so we can choose a cross-section which is spatial, is 3-dimensional. And so that our assumption is that that has no boundaries. But that allows both the possibilities of being finite or infinite. And so there are 2 ways in which we have different curvature and topology. Okay, well, there are 2 ways in which we can have finiteness or infiniteness. And curvature and topology both play a role. So curvature, okay, we know Pythagoras' law from high school and primary school geometry. But as mathematicians discovered in the 19th century already, there's no absolute reason for Pythagoras' theory to be correct. So you can have a self-consistent, what we call negatively curved geometry or a positively curved geometry. And so if we just think about 2-dimensional spaces, because these are easy to think about, we can have a flat space which could be an infinite flat plane, for example, with Pythagoras' theorem, and you can draw a right triangle with x and y and the square root of x squared plus y squared on the hypotenuse. Or we can go to the surface of a sphere, and we all have good intuition of the globe, so the Earth. And so you can think of the map of the Earth as a 2-dimensional closed surface, and so of positive curvature. And so in this case, the curvature is not 0, and the space is finite, but there are no edges. So it's more difficult to go to the negatively curved spaces, which we can also call hyperbolic. The usual analogy is a saddle shape, and for a simple topology, that's typically infinite. And for developing your intuition of these spaces, and if you want to study it in our cosmology group, you'll have to develop your intuition. You can think of someone at the north, or 2 people at the North Pole, for example, flying out in 2 planes. So the planes are neither going to the left or right, and they're going in straight lines. And at first they will separate from each other, and as they go around the globe, they will pass the equator and they will start approaching each other, and at the South Pole they will meet each other. And they have neither gone to the left or right. So mathematically we say they went in straight lines, or more formally we say they followed geodesics. And so a positively curved space, like the surface of the Earth, is one in which 2 straight lines going from a point will after some time converge together. And the negatively curved space is one in which the 2 straight lines will diverge from each other. So in fact, they will go exponentially fast away from each other. So for the simple topology, the positively curved space is a finite surface area for 2 dimensions, or in 3 dimensions of finite volume. And then for topology, well, okay, so the positively curved case is finite, and the flat case and the negatively curved case is for have infinite surface area or in 3 dimensions volume. But now if we consider topology, because all spaces have some topology, in the flat case, let's think of something that most of you have played, which is video games, where you come out from the right of the screen, come back through the left, or go through the top and come back through the bottom. So the classical game is Pac-Man. But for a game where you go through the top and the bottom, you need something beyond classical Pac-Man. And so this is a perfectly good mathematical space. There's nothing wrong with it. And so if you want to tell your parents that you're practicing mathematics when you're actually playing video games, which are multiply connected, so in which the top and bottom are connected and the right and left are connected, you can play these video games and you can tell your parents with full mathematical justification that you are studying modern cosmology and you're developing your intuition of it. So to go to 3 dimensions, what you can do is take a cube and identify opposite faces. And so in that case, you go through one face, you come back through the other. And so again, that's a perfectly good flat space, which is of finite volume. And then you can do that with the other 2 curvatures. So with positive curvature, there are many possibilities of the basic polyhedron, we say fundamental polyhedron, in which you identify opposite faces. And with negative curvature, again, you can have a fundamental polyhedron to think about this space, and you go through a face, you come back through the other face. And so for any of the three curvatures, you can have a finite space depending on which topology we have. And so getting back to observations, we could to some degree say that one of the big questions of, let's say, the first century, or let's say first maybe, I would say 70 or 80 years of modern cosmology, from let's say the 1920s to around 2000, was constraining the curvature parameters and relating them to the rate of expansion. And so now we have a more or less good approximation. We call this the lambda CDM model. And for topology, so the question of finiteness or infiniteness, roughly from most of the research has been done from the 1990s to today, so just the last 30 years. And in fact, the UMK cosmology group, or Nicholas Copernicus University cosmology group, is one of the main groups that has been working on this. And so you can look up my papers from the past few decades. There are a few other groups in the world, but we are one of the strongest groups in this topic. And so we've been working on this. And the big question is, if we actually manage to discover this, so have evidence of it, then we will know, in fact, which class of curvature the universe really is. And we will also know the volume of the universe and the topology. So far, so to give you the bottom line, so far we don't know it. But this is a huge question for cosmology. We don't have the answer yet, but if you are interested in working on this, come here and we'll see if we can advance on this.
Ale raczej -1, 1 czy 0? Negative, positive, zero, we don't know it.
We don't know. I mean, within the standard model, people say we are very close to flat. But the thing is, very close to flat, I mean, it depends how precise it is. So, in fact, once when I was working with a mathematical colleague, and I said in cosmology, we have this symbol that we say less than or approximately equal to. And he laughed at that. And he said, okay, for a mathematician, what does that mean? If it's less than or approximately equal to, I mean, it could mean anything. It could mean it's less than, equal to, or greater than. So, in fact, we really don't know the curvature. But if we can detect the topology, that would really say what type of space we live in. And that would really say there would still be an error bar on the actual number of the average curvature, but it would really distinguish between the negative, zero and positive classes of spaces.
Czy są jakieś przewidywania, jaki kawałek wszechświata widzimy teraz? Jakiś procent mały, czy cały, czy to też nie wiemy?
The short answer is that we really have no idea. We could give if you want to give if you like, a democratic answer in terms of the research, cosmology research community, probably the big majority, probably 95%, would say that because inflation, which is an early period of exponentially fast expansion, because that gives a reasonably good explanation for many of the observational parameters that we measure. Because of inflation, the minimum size of the universe is probably something like e to the power of 60, so something like 3 to the power of 60, so something like 10 to the power of 30. So something like, cube root of a Google times the scale, maximum scale to which we can observe. So the most popular answer would be that we can observe almost nothing of the universe. But then there's also a problem in terminology, whether we mean the whole universe in the sense of the model which is consistent with our observations, or the preferred model, or just the universe which is the part which we can observe. Because in that case, by definition, we observe 100% of the part which we can observe. And if we, in fact, can detect topology, then, in fact, we will get a definite answer to that question.
To myślę, że warto się skupić na tym, co wiemy. Na pewno faktem jest, że wszechświat się rozszerza. W jakim tempie? Czy to się dzieje coraz szybciej, coraz wolniej, czy zawsze w tym samym tempie? Jak to wygląda w czasie?
Okay, according to the current standard model, lambda-CDM model, we normally write this in terms of the Hubble constant. So normally we say 70 kilometers per second per megaparsecs. But in fact, if you simplify that, that's roughly 0.07 per gigayear, because it's in units of inverse time. So a gigayear is, of course, a billion years. So every billion years, if you take a given piece of the universe, then the current rate says that should be about 7% bigger after 1 gigayear, after 1 billion years. And that is the same in each piece of the universe. And so that's the first, okay. I haven't said anything about the scale factor so far. So the standard model says that the whole universe expands in a way that is exactly proportional. And so we have a dimensionless parameter that we call the scale factor. So by definition, we say the current value is 1. And so the Hubble constant, in fact, is the derivative of A divided by A. So A dot over A, or dA dt over A. Since the current value is 1, so the current value is dA dt divided by 1, which is dA dt. So the current value of A dot is this 0.07 per gigayear. And you can take the second derivative, so A double dot. And so A double dot is currently estimated to be positive, so there's acceleration. So in that sense, the second derivative is positive, so there's acceleration of the scale factor.
Czyli ten wszechświat się powiększa. Czy on zawsze się powiększał od samego początku istnienia, czy coś się zmienia w tym wszystkim?
According to our current model, yes, it is always expanded.
Dla mnie jest to strasznie nieintuicyjne, bo właśnie my żyjemy tutaj lokalnie, widzimy, że wszystko ma się dobrze, nic się nie oddala, skale są długoczasowe, dlatego może tak się dzieje. Czyli my jesteśmy w stanie dość dobrze matematycznie opisać, jak to się rozszerza, prawda?
Well, right at the moment, yes, but as we go backwards towards t equals 0, so you can either use the word Big Bang to either mean t equals 0 or to mean the whole model, so it's ambiguous. But if we go towards t equals 0, the universe gets more and more dense, it gets hotter and of higher and higher pressure. And so the model gets more and more theoretical and hypothetical. So going back towards what we call the cosmic microwave background epoch, so where there are, the universe was roughly 1,000 times more contracted in each of the 3 spatial dimensions compared to now. That's the cosmic microwave background epoch. So there were not yet any galaxies. The density perturbations on what we say is a co-moving scale of 100 megaparsecs was something like, we say 10 to the minus 5, so 0.01%. So the universe was much more uniform than now. So at that epoch, there were not yet any galaxies. But still, that epoch was that's still the physics that's reasonably standard. So we have nuclear fusion and so on. In fact, we go a little bit earlier than that to, that epoch was when the universe was a few 100,000 years old within the standard model. We go back to the first few minutes, the first few seconds, that's when we have nuclear synthesis. So, when single protons joined together with neutrons and made the first helium nuclei. When we go much earlier than that, that's when we go to grand unified theories. The universe you have to use models of physics which are more speculative. when we get to the epoch of the age of the universe being 10 to the minus 34 seconds or so, then we need to apply quantum mechanics and general relativity at the same time. So then the universe is really speculative because we don't yet have an agreed upon theory of quantum gravity. So there are many very good people who are working on ideas of quantum gravity. So there's causal dynamical triangulation. There was a Polish researcher, Jurkiewicz, who died 3 or 4 years ago, who was one of the top experts in this. There's also loop quantum gravity. To me, I don't know these, I just know about these, so I've heard lectures on them. But to me, these seem to be two of the more interesting approaches. There's also, membrane theory and M theory and string theory and so on, which I'm part of the group which is more skeptical of these without actually knowing it, but I'm skeptical of it. But in any case, probably I know at least the loop quantum gravity approach goes beyond t equals 0, so it goes to earlier epochs. So that goes earlier than t equals 0, and we call that a big bounce. And so there was a universe which was, contracting before the early epoch, and then after there was the expansion of the part of the universe that we can observe. So there certainly are people working on this. Probably it's better than science fiction. So this would depend on where you lie on the spectrum from observational cosmologists to theoretical cosmologists. The observers would probably call the pre-Big Bang models science fiction. The theorists would say that this is deserves the word theory. I only do observational cosmology, and I'm interested in things which we think can be constrained by observations in the reasonably foreseeable future. It could be the next few decades, it might be a century from now. And so for me, I'm aware of these other efforts, but I don't work on them.
Często przy tych tematach pojawia się pojęcie ciemnej energii. Czy faktycznie, bo nie wiemy co to jest, ale czy faktycznie ona jest potrzebna do opisu modelu wszechświata?
Well, strictly speaking, I mentioned that we have this standard model and that the second derivative of the scale factor is positive right now. So the scale is accelerating. And so dark energy is really just another way of saying that the current best fit has a parameter in which the universe is accelerating. So this is an approximation. So this is within the family of the standard models, which are uniform, spatially uniform at any given time. We also see isotropic, so the same in all directions. And we call these the FLRW models, Friedman, Lemaitre, Robertson, Walker, after 4 of the main cosmologists who worked on these. So within this family of models, we cannot avoid dark energy. However, we know that these models are not strictly correct. Because, in fact, this gets back to one of your earlier questions, because the universe is not strictly speaking homogeneous. There are underdense regions, the voids, there are overdense regions with galaxies, and strictly speaking, we need to model all of this together. And we need to model that together with the expansion. And in fact, the current approach is to start off with mathematical solutions for the universe being perfectly uniform at each time, and then afterwards saying, hey, we know that the real universe is not uniform, and so we will make a perturbation, and we will hope that this perturbed model still more or less agrees with the Einstein equation. And then there's a small community of cosmologists around the world, especially in Europe, but a little bit elsewhere, who want to apply the Einstein equation to expansion and formation of structure together. And so we call this approach inhomogeneous cosmology. And this approach has the possibility of avoiding the need to have dark energy. So in this dark energy would in fact just be what we call the scientific word is a phenomenological effect. So a more popular word would be, we could say a heuristic effect or a fudge. So from the point of view of inhomogeneous cosmology, it may be the case that dark energy is just a shortcut to say that in the last few gigayears, the universe started to become very inhomogeneous, with voids expanding faster and clusters of galaxies becoming stable, and that when we average this together, we get faster overall expansion and an acceleration. So it could be that dark energy is really just a shorthand way of saying that we live in the epoch of galaxy formation and of void formation.
Dziękuję. Teraz już jest wszystko w mojej głowie poukładane. Myślę, że warto wrócić do początku Wszechświata, bo mamy na to niezbite dowody w postaci mikrofalowego promieniowania tła. Jesteśmy w stanie to zaobserwować. Co ono nam ujawnia? Jaka struktura była początkowego Wszechświata? Czy jest on jednorodny, czy nie jest on jednorodny z samego początku?
Okay, well, in cosmology, when we go backwards in time from now, we generally think logarithmically in terms of time or redshift. So going back to the cosmic microwave background epoch, we only shrink by a factor of 1,000. And so that's not very far compared to going all the way back to the quantum epoch. So in fact, for the quantum epoch, okay, if we go in terms of time, the cosmic microwave background epoch was a few 100,000 years compared to 10 gigayears. That's only a factor of about 10 to the 5, so 100,000. But to go back to the quantum epoch, that's a factor of about 34 plus 17 plus 10, so 27 plus 34. So that's about 61, if I've done that correctly in my head. So 10 to the 61 is much bigger than 10 to the 5. So for all of cosmology, if you want to go to the quantum gravity people and loop quantum gravity, that's much further close to zero, and that's where you have the pre-Big Bang epoch. But getting back to your question, I appreciate this question because this is getting back to real observations. So that's only a factor of 10 to the 5 in time. And so in length scale, it's a factor of 1,000. In terms of density, it's a factor of 1 billion. Because there's 1,000 this way, 1,000 this way, and 1,000 this way. Much more compact. Okay, what does that tell us? Okay, the radiation that we observe, so observationally, it came from about 10 gigaparsecs away, or, 10 h to the minus 1 gigaparsecs, or let's say 14 gigaparsecs. So it came from, observationally, we can think of a sphere around us. That light started moving towards us. So in fact, from an observational point of view, this is very anti-Copernican. From the observational cosmologist's point of view, we are at the center of the universe. And that is just a consequence of the fact that the speed of light is finite. So from this observational point of view, we can think of all these photons, the cosmic microwave background light was destined to come to our telescopes. But in reality, from the theoretical point of view, the light was going in all directions because there was an equilibrium of photons and protons and electrons and neutrons going in all directions. But from the observer's point of view, it's only the ones which were destined to come to us, which are the ones we see. Okay, so what's good about them? The first good thing is that to our first approximation, this light is very, very uniform. And so we say isotropic. So that's consistent with the hypothesis of this family of models in which the universe is almost the same everywhere. Of course, that's quite some time back in the past, but still it's consistent with the model. So that's a good level of self-consistency. And then if we look at this map of this radiation in more detail, well, okay, the second thing is that if we look at this radiation as a function of frequency, we find that it follows what we call the Planck spectrum, which is in the end of the 19th century, it was a, partly observational, partly theoretical model of how much light there should be at different frequencies if there is what's called a black body. So if you like, you can think of a box, and inside of it, the walls are black, so light cannot escape or enter. And you have some measuring instrument, and you'll see an equilibrium depending on the temperature of photons and the molecules. And so you will see a certain average. If you draw a diagram of the amount of light at different frequencies, more or less you'll see a curve, something like this. And there is a formula which says exactly what this curved shape should look like. And what we first observed with the COBE satellite, so 1992-1993, is that the spectrum was very precisely following the shape as a function of frequency. And so that was consistent with the hypothesis that there was this equilibrium generated physically by the universe between protons and electrons and neutrons and photons, and just this statistical equilibrium. So all of this was very nicely self-consistent with the model. And after that, if we go back to the map as a function of direction in the sky, if we subtract off the average value, we get a map which is a bit stronger in one direction and a bit stronger in the other direction. And that's consistent with the fact that we live in a galaxy which has a bit of some speed with respect to this average reference frame. And if we subtract off what we call the dipole, then we get some effects which are from within our galaxy, the plane of our galaxy, because we live in a disk galaxy. But on the high galactic latitudes and high positive galactic latitudes and high negative galactic latitudes, we see fluctuations. So some places where there is a bit more light and somewhere there's a little bit less. And already in these observations by COBE, we found that this statistical distribution was consistent with the fact that the universe was not perfectly uniform. And this is what we need, because we need some perturbations to grow so that the initial small density perturbations could grow by gravity, or local gravity if you like, and become more and more overdense and eventually collapse to form galaxies, and the underdense regions had to form voids. And so the fact that we observed these perturbations in the cosmic microwave background, that was nicely consistent. It was roughly consistent with the fact that we need to form galaxies in order to have a self-consistent model of the universe. But that's with a caveat that this model is still fudging a little bit, because it's the uniform model and adding on perturbations afterwards. So mathematically, we still have work to do to have a fully self-consistent model of nonlinear structure formation consistent with Einstein's model of gravity in the cosmological context.
Dobrze, że jest jeszcze coś do pracy, bo byłoby nudno. Mamy perfekcyjnie omówiony początek. Wiemy, co się teraz dzieje. Do czego to prowadzi? Jaki będzie koniec? Czy będzie ten koniec? Jak to się wszystko skończy?
To me, that's science fiction. There are too many uncertainties in the model to really say. If we take the current model, literally speaking, and extend it into the future, then the scale factor as a function of t will approach e to the t with a constant factor times the t, so an exponential function. So it will expand faster and faster according to this model. And so galaxies will be further and further away from each other, and so people refer to the heat death. And And so, well, I haven't tried to put numbers in this, but on the scale of hundreds of billions or trillions of years, the question of how civilizations would exist and where energy would come from gets very difficult. But the thing is, even with the last 1 or 2 years of data, we're already starting to have evidence that the standard model, lambda-CDM model, is not quite right. And in the next 5 to 10 years, we have the Foremost survey, we have Euclid, we have the Rubin Observatory, and legacy, it's called LSST, and there's a backronym which I forget, but it used to be called the Large Scale Structure Telescope. But anyway, the LSST and Rubin Observatory, also Euclid, with all of these projects, DESI, we are going to get a lot more constraints on this. And so the lambda-CDM model itself is probably not likely to survive another 10 or 20 years. There are going to be new variations on it by that time. And so in that case, trying to predict the long-scale future will be, as I said, science fiction. But just for completeness, there are models where the universe expands to a maximum value of the scale factor and then shrinks and then goes to a big crunch. And so then, of course, if you think that some of the big bounce models are correct, you could go to another big bounce and there could be another expansion afterwards, and so there could be an endless cycle of bounces and crunches. Well, crunches and bounces. But I would say that that's on the very theoretical side of cosmology.
Czyli wtedy by się okazywało, że jest coś przed wielkim wybuchem, bo to by oznaczało poprzedni wszechświat, prawda?
Well, that's possible in the quantum cosmology approaches, such as loop quantum gravity or causal dynamical triangulation.
A co z tymi miejscami, które są nie do końca poznane? Mam na myśli na przykład czarne dziury, które są wyjątkowe, jeśli chodzi o czasoprzestrzeń. One pokazują, że ona nie jest ciągła, prawda? Że tam coś się dzieje.
Well, again, with the standard cosmological model, if we take the current model and take it literally, then the t=0 moment is not part of the model. So mathematically, this is called a singularity. So for mathematicians, that's no problem. It's like the hyperbola, the function y=1/x. At x=0, there are no values. It's just undefined. So mathematicians say there is a singularity, that's no problem. The two parts of the hyperbola are separate, and that's it, there's no problem. For a physicist trying to say that a hyperbola is a model of the real world, they will say there's a problem because we want to know what happens at x=0. So for the cosmological case, as I've been saying, if we try to go towards t=0, the model gets more and more speculative, and then there are various extensions which are proposed, and they generally avoid the t=0. For black holes, okay, I don't do much with black holes, but you really have to ask the same question. If you take the simplest model of a black hole, which is the Schwarzschild solution, in that case, there is only one black hole in the whole universe. And in fact, there's no mass in the universe because the center of the black hole is not part of the model. And so there is a value m, so we can say that the black hole as a system, the spacetime has a mass, but in fact the density is 0 everywhere. So the standard terminology in physics is that it is a vacuum solution because there is no density anywhere, but it has a value m which is positive. So you cannot seriously take that as a model of a real black hole because the black hole does have a mass, and normally for stellar mass black holes, we think they form from the late stages of evolution. For supermassive black holes at the centers of galaxies, we have various ideas of how they might form. They could, to some degree, be primordial from the very early universe, or they might be formed from stellar massive black holes which merge together and successively make black holes which are of higher and higher masses. The other thing is that black holes, stars have some spin. So because if you have mass which is distributed on a large scale, which has nearly no rotational movement, typically it's going to have some rotation. And for conservation of angular momentum, as you have something which is rotating very slowly on a big scale, if you shrink it together, it's like a ballerina. So moving slowly and then bringing her hands in closely will spin very fast. So typically we expect black holes to have some rotation, and so then you need to at least go to a co-model, which is more complicated. And then for the formation of stellar mass black holes, you have to take into account the fact that there is some mass, non-zero density in the inside. So things get more and more complicated. So whether or not there's a true singularity in black holes is, to me, I'm not sure if a black hole, to what degree people who study black holes take it really seriously, but certainly the real models, it's really only a philosophical question whether there are true singularities at the centers of black holes or not. So to me, there was a recent comment by Roy Kerr saying he thinks there are no true singularities in black holes, and to me that seems a reasonable approach. But what we measure are the event horizons near black holes, and so certainly those exist. But if you want to play a language game, you could actually argue whether or not black holes exist, because whether they have true singularities or not is probably something we can never actually measure. But whether they are things which match the black hole model very well, that's something which is established.
Wydaje się to bardziej skomplikowane niż z początku. Często rzuca się razem ciemną materię, ciemną energię, trochę przejdziemy na luźniejsze tematy, ale jest zasadnicza różnica pomiędzy tymi dwoma rzeczami. Czy ta ciemna energia, czy jak myślisz, ona będziemy w stanie ją kiedyś odkryć, zobaczyć? Tak fizycznie, czy nie?
Well, at the moment, I am probably 50-50 with the hypothesis that inhomogeneity explains dark energy. So in other words, that dark energy is really just the epoch of void formation. But this still has to be worked out. If you try to have a democratic point of view, which of course doesn't say what the long-term scientific point of view will be, but a democratic point of view from the cosmology research community would be that there is a huge range of proposals for what dark energy is, and we really have almost no idea of what it is. People are trying to constrain it, and people who publish particular papers on ideas of dark energy hope that their idea is the right one, but really we can't say.
Czyli musimy pogodzić się z faktem, że ona istnieje, że jest, tak ją nazywamy, ciemną energię i ciemną materię, no i zostaje nasza normalna materia, galaktyki, tutaj cała materia, którą możemy jakkolwiek opisać.
Oh, sorry. Well, actually, there I was just going for dark energy. For dark matter, that's the characteristics of that. It's very different to dark energy. And in fact, you mentioned Newtonian physics earlier. A lot of the arguments for dark matter are on the scale where Newtonian arguments are more or less correct. So, for example, roughly on the scales of a few or tens of megaparsecs, so a few or tens of thousands of light years. So roughly the movements of galaxies, roughly speaking, we can get equilibria between the speed of galaxies moving, their masses, and the distances between them. So roughly speaking, that gives us a constraint on how much dark matter there can be. Roughly speaking, it's about 30% of what we say is the critical density, so the amount of density to give us a zero curvature or flat universe. And so these constraints would be hard to explain by inhomogeneous cosmology, although there's some suggestions that we might be able to explain it, but they're not too promising yet. For dark matter, the particle physicists, in fact, for 20 or 30 years, have said that there ought to be new sorts of particles. So they've had lots of hopes for explaining it. Nothing significant has been detected so far, but the field is still open to make a discovery of dark matter particles on many scales. So I guess I'm sort of expecting that there will be a direct observational detection of dark matter, and that will be, in some sense, that will be the more ordinary question, and as opposed to like energy, which at the moment, my tendency, but again, I said it would be about 50-50 at the moment, would be that it's just the epoch of galaxy formation or void formation.
Za mało miejsca jest w głowie, żeby to wszystko pojąć. Uniwersytet Mikołaja Kopernika. Pracujesz tam w roli właśnie profesora. Czemu wylądowałeś tutaj u nas, w tym miejscu, w Toruniu? Co było takiego atrakcyjne, żeby tutaj przyjechać i móc się spełniać zawodowo?
Well, I already knew some of the main Polish cosmologists, so Roman Juszkiewicz, Staszek Bajtlik, and, well, I've done many postdocs around the world, so at the Ayuka in India, at the National Observatory in Japan, at Sussex University in England, and it was about time to, well, also the IAP, the Institut Astronomie de Paris in Paris, in France. And it was about time that I ought to get a fixed position somewhere, in a faculty position. And so Roman and Staszek said, okay, hey, why don't you come to Poland? It would be a good place. There's some very good groups here. And I said, yes, there are some good places here. And so they proposed that I apply, and I applied, and I won the competition. So I was given a faculty position here in Toruniu. And so I found that it's a good group. It's been developing well since then. So it's a good astronomy group. We have a good radio telescope, 32 meters. There's a physics faculty doing many things, such as using timing measurements to potentially detect gravitational waves in the laboratory. There's, in fact, some very good mathematicians in the mathematics faculty. So overall, it's a good environment.
Cieszę się niezmiernie, że Toruń UMK jest na tyle atrakcyjne, że faktycznie można się cały czas spełniać zawodowo. Czy nauka jest jedną rzeczą, ale tutaj też jest edukacja studentów, ludzi, którzy chcą wejść w tę dziedzinę. Czy jest tutaj miejsce na to? Czy jest dobre to miejsce na edukację?
Well, I'm not really objective to answer that, so you'd really have to ask other students. And today, with so much internet access and social media networks, well, there are participatory free software, social media networks, decentralized ones, like the email system. There are also the centralized ones, but you have lots of ways of accessing knowledge about us. As far as I know, the students, well, there's a variety of students here, a mix of different students. So this year I've had my first, in the past academic year I've had my first group of the PANDA students, so the international group. They have seemed happy here, so I guess you should talk to them and see what they think about it.
PANDAS means physics and astronomy.
Physics and astronomy, yes, that's the jargon of this particular program.
Dlaczego astronomia? Kiedy ten wybór padł na tę dziedzinę? A czemu nie fizyka na przykład?
You mean for me personally?
Yeah.
In fact, this was when I was looking for my honours year project, so the equivalent of the master's year, where I did my undergraduate and PhD at Australian National University in Canberra. And in fact, the lecturer I was talking to, he said, okay, well, for a project, it depends what you're interested in. And I said, the problem is that I'm interested in everything. So this was Dayal Wickramasinghe. And he said to me, Boud, I think you're a cosmologist. And it turned out he was right.
Czyli nie zamieniłbyś na inną dziedzinę. Ta kosmologia jest tą jedyną dziedziną.
Well, in some sense, no, I wouldn't change. But the point is that cosmology is a study of everything. So it includes everything. So this allows me to do research in every field. So in fact, I've done a few articles in statistics, because in astronomy statistics, well, we constantly have to check how serious our data is in observational analysis, in doing models. We constantly have to be suspicious and ask ourselves, did we do something wrong? And every now and then, something goes wrong and there's something odd in the data. And so there are things like Poisson statistics. And so, for example, I think all astronomy students, by the time you get through your PhD, Poisson statistics are second-hand. And so if you don't get noise of something like the square root of the number of counts, then you know that there's something wrong. And so in fact, it was in 2009, the Iranian presidential election, that I noticed something was odd. And after in the COVID-19 pandemic, I noticed there were some odd statistics. And nobody else was publishing analyses of these, so I did some quick analyses and I proposed them for peer review in some professional journals, and they got accepted. So for me, it's part of cosmology because, sociological processes such as elections, biological, sociological processes such as pandemics, that's all part of the universe. So I did a little bit of side research. These research papers were given to independent researchers for peer review that are accepted. So in fact, cosmology does extend to all knowledge. And in fact, this video itself, or podcast, is going to be distributed through the internet. And the knowledge for astronomy, it goes from the real observations on telescopes. It goes through models which are based on mathematical ideas, which mathematicians talk about on blackboards and with scribbling with chalk and pen on paper. But then they get coded into software and coded into files, both from the theoretical side and from the observational side. And what I hope that my students get to see is the full chain of reasoning from raw theory, raw axioms, and from raw observations through to the final thing. And you need to understand the full spectrum of this. And so, in fact, that's why this video itself, you will statistically most likely see it on YouTube, but I recommend that you search for it on PeerTube, which is a decentralized federation of distributions of videos, because this is more likely to get knowledge which can be verified by humans and human networks and human groups than on YouTube, which is more centralized. And we all know the problems of centralized organizations. In fact, Poland has had a historical problem with communist governments and many occupations by neighboring countries with very centralized governments. Today, Poland is, there were the past 8 years, according to the DemV political scientists of Poland, was, we say, a backsliding democracy. Next year, we will see the new analyses, whether it is returned to forward-sliding democracy again. But it is within the European EU context. So for looking for knowledge in this open community environment where you can be critical of things, which is not too centralized, this is the sort of thing which I think you can expect to find at Nicholas Copernicus University and within the cosmological context. And it's something that should be open for debate, but open for debate based on files and based on evidence, and where we can look at the chain of where this all comes from. And always based on subject to peer review.
Ależ my dzisiaj ja osobiście się dowiedziałem wielu rzeczy. Mam nadzieję, że słuchający nas Państwo również słuchali tego z zaciekawieniem. Dziękuję ogromnie za dzisiejszą rozmowę. Ona rozświetliła mi wiele w mojej głowie. Kosmologia zawsze nie była moją mocną stroną. Mam nadzieję, że też Państwo z zaciekawieniem słuchali tego tutaj, co było powiedziane. Dziękuję bardzo. Mieli Państwo okazję słuchać profesora Bouda Roukemę. Zapraszamy na kolejne odcinki podcastu Wgryzamy się we Wszechświat.
Okay, so thanks, David, and thanks to you, the audience, and terima kasih, and Daniel Wad.